All right, hi. My name is Tomo. It's after lunch. It's like the low energy time of the day. I'm very flattered and gratified that you all chose to be here instead of any of the other glorious sessions that we have in this slot. The room is packed, so I hope that you managed to be comfortable. Because for the next 40 minutes or so, we're going to be talking about microservices. Now, microservices is not exactly a new subject. It's been discussed in hundreds, maybe even thousands of blog posts, conference talks. People have been writing books about it and discussing it in every which way for upwards of a decade. So this is very far from being a new subject. And just having this many people in the room tells me that this would be a good opportunity to stop, take a deep breath, take a step back, and look at microservices as a topic with a fresh perspective from the point of view of a decade of industry experience building and running systems in that particular architecture. So our menu for today includes a short recap on why we even do microservices, what it is we hope to get out of them, what we as an industry have managed to learn following that decade of building these systems, what we as an industry, I feel, have failed to learn that I think might very well be more important, and my own personal opinion or take on what it is we should or should not be doing in order to continue realizing the benefits of this architecture moving forward. Despite my usual inclination of not introducing myself, in this case, I think a short introduction is in order. So who am I? My name is Gabel. I come from Israel. I'm an occasional public speaker. I'm a software engineer at WeWork. Prior to WeWork, I had spent 5 years at a company you may have heard of called Wix that is very much a proponent and early adopter of microservice architectures. Before that, a bunch of other companies, most of which ended up with a microservice or microservice-like architecture. I like to style myself a technology malcontent, means I have very strong opinions that oftentimes go sort of against the grain of accepted or common wisdom in the industry with respect to various things. Specifically, that right there is me railing against dependency injection. But in this case, I'm not actually gonna inflict a 40-minute long rant on you, but instead I'm hoping that the reason I'm telling you all of this predominantly is not because I'm smart or cool or any of these things. It's because I'm reasonably old and I've seen a bunch of companies. I have seen microservice-based architectures fail. I've seen them succeed. I think it gives me a reasonable perspective to draw some conclusions that may or may not be of benefit to you. Hopefully they will. So let's get started with a little recap, right? Microservices, not a new thing, but I think it's worth revisiting why it is we do microservices in the first place. So if you've been consuming the sort of material that's been around for the last decade with respect to microservices, you will probably end up thinking microservices are a thing we do for 3 major reasons. The first reason is developer velocity. The assumption is if you have a business, you have a large system, you have a large business, and you manage to take that business and decompose it into smaller bits, right? If you can break down your business into separate, shall we say, sub-businesses or subsystems, domains, you can call them what you will, and you manage to build a strong wall around each one of these domains so that they can be dealt with independently, you have gained some value. You have gained developer velocity. You have gained the ability to independently release different parts of your system. You have limited the scope of work for any particular group of people, be it a team. And as we all know, working on fewer things is easier. It means you can move faster. It means you can reason about those things better. And it leads to stronger decoupling, which means teams can move forward independently and a lot quicker than they would in a traditional monolithic architecture. Now, it's important to note that you can only realize these benefits if you actually manage to take your business, to take your system and break it down into truly independent things, truly independent substrata that you can actually build a strong wall around, and that wall keeps things in order, keeps things moving fluidly forward. In the DDD world, we like to call this bounded context, right? And bounded context is the driver. Bounded context is sort of the prerequisite that you have to realize any of the perceived benefits of microservices, starting with increased developer velocity. The second major reason why we do microservices is scalability, especially for early adopters that were sort of writing and producing talks about this subject in the early years of this decade, the Twitters of the world, the Netflixes of the world. One of the things that commonly comes up is the ability to scale your system better. If you can break down your system into these independent parts, you can start independently scaling these parts. You can choose independent storage. That is, again, assuming you have made the sensible choice of disallowing every one of these components from accessing the storage of any other subsystem. So you can choose the right tool for the job. You can choose different storage engines. You can scale your storage independently. You can scale your services independently. And you realize a greater total scale for your system. There's also the fact that any system that's reasonably small is much easier to optimize than a big system that does a lot of different things. As any database administrator will tell you, it is much easier to take a small database with a small set of tables and optimize that over one large instance that contains many, many different use cases, many different pieces of functionality for different services. It's just that much easier to optimize. And again, you can only realize that benefit if you actually manage to have bounded context, if you actually manage to break down your system and have those very high walls between the different parts. The third canonical reason why why the industry has been moving in that direction is resilience. The assumption is, with a system that's broken down into many independent parts, you have much better error boundaries between the different parts of your system, and the system becomes more resilient, or at least potentially more resilient, to partial failures. The canonical example for this would be Netflix's recommendation engine. Let's assume you're a Netflix user, as I imagine a lot of you are. Let's assume you have a particular show that's your favorite, say Lucifer, which, by the way, is in my opinion, a terrible show, but to each his own, right? And when you go to Netflix.com or you start your Netflix app on your Android TV or whatever it is that you do, typically you have a recommendation engine that gives you a personalized recommendation for you, right? Because you have watched Lucifer, you may be interested in insert your favorite other terrible set of shows. Crucially, though, if the recommendation engine fails, right, the recommendation engine is down for whatever reason. Does that mean Netflix is down? Just because Netflix can tell you that, you know, because you liked Lucifer, you may like this other thing, does that mean you don't get to watch your favorite show? Obviously, that would be a terrible user experience. But in a traditional monolithic app where you have everything stuck into one single application that's, you know, deployed on multiple servers, and you have one monolithic database that serves all of your needs, it becomes so much harder to deal with issues independently that, in effect, any major issue will bring your whole system down. So a distributed system, a non-monolithic application, generally has the opportunity to deal with these partial errors in a much nicer, more streamlined way. Now, there are also ancillary or secondary benefits to using microservices. The two most touted ones are polyglot development. In other words, the ability to develop independent parts of the system in different tech stacks, different languages. That is obviously something you can do in a microservice-based architecture and is obviously impossible to do in a monolithic app. The other claim is that a microservice-based system is easier to test. Now, I don't have a strong opinion on this. I think it might be a spurious argument, but then there might also be a point to it. This is all sort of ancillary to the set of things I want to talk about, so we'll not be delving into that. But these are the claims. And once again, with all of these things, you can only realize these benefits if you actually have that bounded context in place. So far, so good. This is, I hope, a reasonably complete recap of why everyone seems to be all gung-ho about microservices and had been for the past decade. My first quasi-controversial opinion is that we don't actually do microservices for any of these reasons. It's all about organizational scaling. Microservices are an enabler for organizational scale. Allow me to explain. Take any software company, right? Any successful software-based product company. Let's assume, once again, it's a startup, it's successful, it wants to grow, right? No software company that I know of, no business that I know of is content with having one successful product and then just going into maintenance mode, firing most of the staff, and just keeping that product alive until it becomes irrelevant and dies off. A successful organization generally wants to make more products, wants to grow, it wants to make more money. In order to build more products, you generally have to have more developers, and you have to form teams of these developers. And those teams become increasingly more and more interdependent. You have in a successful organization, you also have issues around visibility. So for instance, if you look at Twitter, when they started off and they failed, no one cared, right? When you have a few thousands, a few tens of thousands of users and you fail, no one notices. But with success, with the millions of users that Twitter has, if you remember way back, let's say 8 years ago, Twitter would fail constantly. It got to the point where we as an industry, I hope we've started forgetting that concept of the fail whale that you would get when Twitter broke, which happened fairly often. Right? You have lots of users, those users care. They want to use your system. And if your system is unavailable, it's gonna matter. So that's visibility. The other side of the coin is liability. So let's take Facebook, for instance. When Facebook was a small startup that had 100,000 users, no one cared what sort of experimentation they did on their newsfeed or what algorithms they're running or whether or not they do sentiment analysis and try to adjust the newsfeed. No one cared because it was small. But a billion or so users later, suddenly you have congressional hearings about the very same experiments that they're running. Suddenly everyone cares. The company becomes liable. So all of that converges to your software engineers having more and more responsibility, right? More products, more interdependence, more visibility, more liability means more and more responsibility is sort of thrown into the mix of your everyday software engineering lives. Crucially, as you grow, typically what happens with any software company is you have a product and then you either build a second product that shares a lot of the same code and a lot of the same infrastructure as the first product, or you have a main product and an ecosystem of sort of ancillary secondary products around it. Right? It is exceedingly rare for a software company to have 2 or more completely independent, completely unrelated software products at play. So the products themselves become more and more interdependent. They rely on each other to actually get the value to the user. And so do the team. Interesting. And so do teams. Right? The teams themselves become more and more interdependent. They rely on the work done by other teams within the organization to get their work done. And that incurs a synchronization cost. Now, this shouldn't be news to anyone, especially given Adam Thornhill's excellent keynote yesterday, which talked about exactly that. Synchronization is the productivity killer. Let's delve a little bit into that. You might say, so what? You have more products, more teams, more software, more interdependence between the teams. That doesn't necessarily sound like a bad thing. So let's take a look at one of the very few sort of industry academy research done by industry in conjunction with academy. And this is in this book called Accelerate, which tried to take a quantitative approach to DevOps. Now, there's a lot of different things in this book that I'm not going to cover, but crucially, they've identified 4 metrics that they have found a strong correlation between those metrics and what they call highly productive or highly successful organization, the Googles of the world, the Netflixes of the world. Those metrics include lead time, i.e., how long does it take from what unfortunately came to be called ideation to execution, deployment frequency, mean time to recovery, like given an issue that you have in production, how long does it take to recover service for that particular issue, and change fail percentage, which is how often do you deploy things that are broken. And you will notice that each and every one of these metrics is negatively and severely affected by synchronization. If you have an issue in production and you need to start synchronizing between the teams to figure out who owns that issue, like where in your microservice architecture, your microservice strata, that issue exists, that's a synchronization cost, right? And that's just one example. Every single one of these metrics is severely and adversely affected by synchronization. In other words, what we're shooting for, in order to grow our organization, what we need to do is we need to strive for minimal synchronization between people and between teams and maximum independence. We need our organization to be comprised of teams that can move independently, that don't have to wait for anyone to get their work done. Least synchronization, maximum independence gets you organizational scaling. And it turns out that microservices are sort of intrinsically a great fit for that, because a microservice-based architecture fundamentally is about minimal synchronization and maximum independence of teams. Let us, again, take a deep breath and start considering what it is that we've learned as an industry with respect to microservices, right? Take 10 years back, what lessons have we as an industry fully internalized about microservices? The first lesson is that small is good. Again, tying back to the keynote from yesterday, we know that humans are terrible at maintaining large states in our head. That's what computers are for. And therefore, the less you have to keep in your head in order to get your work done, the better. Also, less code means less bugs, right? That's obvious. But really, what we want to be focusing about is smaller interfaces. What we want is for our systems to be comprised of many, many smaller systems, again, that can move independently. And the smaller the interface, the smaller the API surface area of each and every one of these components, the easier they are to reason about. Small interfaces are good, right? Whatever language you work in, typically, if you go into an interface definition and there's, whatever, 3 methods in there, it's almost trivial to figure out what the interface is about and what it can do. And it's also easier to evolve it because there's less cruft, there's less technical debt, there's less esoteric use cases involved. You need to keep less stuff in your head in order to reason about and evolve those interfaces. And I will add that it's not easy. It's a lot of discipline, a lot of work to keep those interfaces small. There are trade-offs involved. You may have to forgo small interfaces for performance reasons, for instance, or because you have an annoying boss that keeps asking you for new features yesterday. It takes a lot of discipline to keep those interfaces small. But if you manage to keep those interfaces small, you will have realized the benefits of smaller systems. You will be able to deal with those systems independently. And this all results in lower coupling within our systems. And that, I feel, is one of the lessons we as an industry have learned. And when I say small, one thing that drives me nuts is that we are still occasionally having these discussions about what makes a microservice micro. Is it 20 lines of code, or 200, or 2,000? Is it a 2-pizza team? Is it a 5-person team? Maybe it's just having up to 3 endpoints in your service, or maybe 1. All of these discussions are totally useless. They're proxy metrics at best. They don't give you what you want. What you want is a minimal API surface area. Pardon. And that, by the way, is also the reason why you should never, ever share data stores between your services. I think that there had never been, or I haven't yet run into a solid explanation of why that's a good practice, even though intuitively everyone sort of agrees on that. It is because if you share your database, you have expanded your API to include SQL. And SQL is not a small API, right? So you want to keep your API small so that the system can evolve independently of other systems so that you retain lower coupling. Next, Polyglot. The great promise of microservices, especially for older material coming out of early adopting companies, the great promise is if you build a microservice-based architecture and you keep your interfaces lean and simple and cross-platform, that's why HTTP and JSON are so successful. The idea is you can have as many tech stacks as you want. But it turns out that you're not actually going to need it. So this is kind of a best faith effort, like a half a day or so of Googling on my part to try and figure out how many independent backend tech stacks each of these companies has. I don't know how accurate it is because it's not the sort of thing you can just go ahead and ask. But I want to point out that with one outlier, which is Facebook, each and every one of these fairly substantial, very successful companies has 3, 4 tech stacks. Google, with their, again, Googling, I don't know if that's true, 30,000 or so software engineers have 6 tech stacks. This gives us a nice rule of thumb. If you have more than 1 or 2 tech stacks per 5,000 engineers, you're doing it wrong. You just don't need it. More importantly, though, you're not actually going to want it. And I'm gonna rail against this because as a highly individualistic person, I hate technology decisions being dictated to me by the organization. I like to pick the right tool for the job, but it turns out that there is a lot of overhead inherent in having multiple tech stacks, and very few organizations actually do that. And even when they do, they usually end up a few years later converging on a very small set of tech stacks. Because if you have a small set of tech stacks, you can actually mobilize people between teams. It makes hiring easier. It makes helping out a fellow team member from a different team possible. Because if you're building in Ruby and the team next door is working in Go, you're not actually going to be able to help out, and you're not going to be able to move between teams very rapidly because there's a huge learning curve involved. So it turns out that for the most part, you're not even going to want to have that sort of freedom that comes with microservices. But it sure feels nice. I really wish this was more relevant to real-life software engineering, but in effect, hardly anyone does that. I'm sure some do. I'm sure some are very happy with it. But as a rule of thumb, you're not going to need more than 2 or 3 tech stacks in your back-end systems. So just to repeat for everyone, the upshot of this is if you pick quote unquote a wrong tech stack, having a microservice architecture does allow you to replace that moving forward. And that's kind of true. Hopefully you did not select a tech stack you regretted, but that does happen. Another thing we've managed to learn as an industry is that Conway knew what he was talking about. So here's a traditional quote from Conway. Fundamentally, though, the intuition around Conway's law is whatever you end up doing, the organizational structure and the structure of your system architecture will end up looking the same. And you will note that I didn't say one derives from the other. They both can try to move independently, but over time they will converge. So that tells us that you need to structure your teams in a way that reflects the architecture that you want and vice versa, because they're going to end up converging on the same structure. And that tells us there are a few common danger signs that I think as an industry we've learned to recognize and deal with. 2 common danger signs for, shall we say, violating, quote unquote, Conway's law are a data store that's shared between multiple services. I hope it's pretty clear why that's a terrible idea. But something that does still happen, but I feel we've learned to recognize and deal with more and more, is a single system or a single domain of responsibility that's shared between multiple teams. And that is also a terrible idea because it means that there's a diffusion of responsibility and increased synchronization in order to move forward in that particular domain. So if you're violating the single responsibility principle in your architecture or in your organization, you really have 2 options. You can reorganize your services to match the sort of organizational structure that you want, or vice versa. because they're going to end up looking the same, and if the way they end up looking is not conducive to your doing business, it increases synchronization cost, it diffuses responsibility, you're going to have a very painful problem on your hands. I think last thing we've learned is that operations matter. This is the impetus behind the whole DevOps movement, such as it is. In order to attain independent releases, in order to allow developers to move as fast as possible with their independent pieces of your system, you need to ship fast. And you need to disallow any bottlenecks that stand between a developer with a commit and that commit running in production. That is why we've been moving progressively from a global release, and it doesn't matter if it's every 3 months, every 6 months, or every day, between a global release of the whole set of things that comprise your system to many, many small, rapid iterations on independent pieces of your system that are deployed independently. We moved from a centralized ops structure where the ops team typically is in charge of deploying your app to distributed ownership. Now we have operations teams providing infrastructure for engineers to actually deploy their systems independently without that throwing over the fence that was so common, say, a decade ago. We moved from manual deployment to full automation because manual deployment is a major bottleneck and a major cause of errors. We moved from static topologies to ephemeral auto-scaled systems. Right, we're running in the cloud, running on Amazon. We do auto-scaling groups. We treat our servers as, what is it, as cattle, not as pets. I think that's the expression. Right, we have learned those lessons. DevOps used to be this new thing that's hard to explain to people. Nowadays, it's almost a given. If you have an ops team that deals with deployments as opposed to infrastructure, you're going to get laughed at, and for very good reasons. Unless, of course, you're doing something extremely esoteric. So DevOps is a good thing. We've learned that. We've also learned that automation is key. We're automating everything. We're automating infrastructure. We have infrastructure as code with Terraform and such. We're automating deployment. We have big deployment orchestration systems that we did not have 10 years ago. Right? We have the Spinnakers of the world, whereas 10 years ago, you would have simply, whatever, copied off an RPM somewhere and installed it manually in the system. We're automating monitoring, we're automating remediation and provisioning, and everything we possibly can, we're automating so that we can move faster. And the reason we care about automating all of these things is we've learned that we want to move faster in the small. We want to have many independent teams doing their work as fast as possible with as few dependencies on other teams and other people as possible. Automation is an empowerment tool. It means your developers can move faster. Whereas 10 years ago, they not only would not be able to move faster, we didn't even know how to build our organizations in a way that allows them to move that fast. So these are all things I think we have as an industry learned. These are all good lessons. And I feel that these are mostly solved problems. The tools might not be there, but the methodology and the perception is. Let's talk about sadder things, things we have not yet learned. One thing we have failed as an industry, I feel, to learn are the laws of physics. We are, in this room, mostly software engineers. I imagine not all of us, but for the most part, we are engineers. If we were asked to design an airplane, we wouldn't imagine trying to design an airplane without a very, very well-rooted understanding of at least Newtonian physics, right? That's Newton, in case anyone was wondering, right? We wouldn't even imagine it, and if we tried, our plane would crash seconds after takeoff. That's assuming it managed to take off to begin with, and it probably wouldn't. So why are we, as an industry, so comfortable ignoring these two people, Leslie Lamport on the left and Eric Brewer on the right? These are two of the people that define the laws of physics for distributed systems as we know them. Lamport did some of the earliest and most important research on distributed systems. Brewer codified the CAP theorem, right? These things define the rules of the reality that we live in. And yet we're perfectly comfortable designing these systems while not fully understanding or not fully intuiting the laws of physics that those two guys on the left gave us, right? And we keep doing that. And we keep telling ourselves that it's not a big deal because we're not really, we're not building distributed systems. I'm just building this client-server thing or line of business app. But we're all building distributed systems. As soon as you have your server in a MySQL somewhere, or you have your iPhone firing off an HTTP request at a web server in the cloud somewhere, once you have two or more moving parts that comprise your system, as we all do, you're building a distributed system. And in a distributed system, concurrency is the key. If you don't have a reasonable intuition around availability and consistency, you're going to end up building production systems that have inconsistent data between data stores, between data centers. They will not scale, they will lose data repeatedly, right? All of these things happen in a lot of the production systems we build simply because, for whatever reason as an industry, we're still comfortable building systems that flat out violate the laws of physics. And that is very, very sad, and more importantly, there's really no reason for that. Next thing. I feel we have failed to learn that because distributed systems are by nature large and disaggregate systems, many, many moving parts that move around independently, we failed to realize that we need to invest in observability. And I think that over the last couple years, this has finally been getting sort of the limelight that it deserves. But we're still very much deficient in the tools and the practices that are required to make sense and reason about the sort of large-scale microservice-based systems that we're building and that we've built. Now, tools are becoming better. 5 years ago, I would not be able to write this slide. 5 years ago, we didn't have these tools. Nowadays, you actually have a lot of open source aftermarket tools that you can employ to gain observability in your systems. You have tracing tools. You have tools for the aggregation and visualization and graphing of metrics. You have centralized log aggregators. You have the Elk stack, and you have all of these aftermarket products like New Relic, etc., that let you gain observability into your system in a sensible way. Unfortunately, that's not enough. Having tools is a very, very good thing because we didn't have those a few years back. But we're still, as an industry, very deficient in the methodology around how to employ these tools to actually gain insight into the systems that we build. In order to make sense of a distributed system that's big, that has a lot of moving parts that are doing stuff independently, we need to have a much stronger approach and much stronger reasoning in order to answer questions such as, what should I even log? Right? If you take almost any production system and you look at the sort of logging statements that are included in the code base, they are, I would say, somewhere between a valiant attempt and utterly useless. Right? We're not logging things that anyone, including ourselves, actually care about. We log because we've been told that we need to log, not because we're planning on these logs to be useful to us in the future in order to debug the system. And that's a problem. We also don't have a rigorous methodology about what it is we should count. What sort of metrics do we care about? What affects our system? What are the KPIs for any particular production system that you need to monitor so that you know when the system is in trouble or that it's outgrowing its scaling envelope for its existing architecture, or any of these things? These are hard questions. There are no easy answers, but I feel that for the most part, most of us have been ignoring those questions for years, and that is a problem. Fortunately, it also seems that there's sort of a movement in the other direction where a lot of us have realized that it's very, very hard to gain any sense out of what's going on in our systems, and that is why we're starting to invest in tools. what should we monitor? And most importantly, the bottom line is, once we have all of that data, we are still severely deficient in methodology about how to make sense of it. Right? We have all these metrics, all these logs, all of these different things coming out of our system. We don't really have, as an industry, a rigorous methodology that tells us what to do about it, what kind of questions we need to ask, how to aggregate metrics. I'm sorry to have to say this, but a lot of engineers and a lot of companies are still perfectly comfortable doing stuff like looking at average response times, which is the single most useless metric on earth. And if you don't know why that's a single useless metric, then you will have proved my point. Right? As an industry, we have still not properly learned to deal with distributed systems from an observability standpoint. And with all of those sort of unfortunate lacks of learning, I think there are still some things we can do today to start improving the state of affairs in our various systems. And although the title is explosive, none of the things I'm going to be talking about for the remaining 4.5 minutes of this talk should come as any surprise to you. But before we talk about my opinion on what it is we should be doing, let's do a quick recap on what it is we're trying to accomplish here. We aim to minimize synchronization and maximize team independence. That is what we want. What's hard for us is to build systems that are safe, that deal correctly with data, that do not violate the laws of physics, that don't lose data or get incorrect data in through faulty designs. We want scalability. Scalability is still not an easy thing to deal with for a lot of these systems. And we want observability. These are the three things we want. And it turns out that we already have some tools that let us design our systems in a way where the two goals are met and the three things we're struggling with are somewhat mitigated. And a lot of those techniques circle around events. It turns out events are your friends, and events make everything that much simpler. If you design your system with events in mind, and I will, of course, delve into what that could actually mean, then you end up with systems that are more resilient, more observable, less wrong, and are actually simpler, that are easier to reason about, easier to think about, easier to build, and easier to deal with. And events come into play in three major ways in sort of systems we end up building. One way we can use events is in modeling interactions between our various services. We all know and love RPC, and some use cases make perfect sense for RPC and very little sense for other things. But it turns out that a lot of the flows that are built into your systems, you can actually model as services emitting and consuming events. Again, this should not be news, right? We've had talks about event-based systems in this conference and in every other conference over the last 10 years. Now, the advantage of modeling the interactions between your services as events being emitted and consumed is that it enforces strong context boundaries. If you only emit events and only consume events, that is the surface area of your service. By definition, you have to seriously consider what the context boundaries for your service are. Right? Otherwise, you just can't reason about what sort of events you need to emit and what sort of events you need to consume. It also lets you, assuming you have a scalable event bus or message broker or whatever it is you use, it also allows you to scale your services independently. If service A publishes events and those events are useful to services B and C, but in completely separate ways, more importantly, services B and C might have completely different scaling characteristics and requirements, you can do that. You can build those services independently, consume the same events, and scale those services in very, very different ways. And because you're emitting events and consuming events, it makes it that much easier to actually observe what's going on in the system, because you can consume those events as part of your observability story. And finally, asynchronous flows also tend to increase system reliability, especially for complex flows. The other way in which you can use events that I highly recommend you look into is essentially event sourcing. Instead of storing your business entities as mutable rows in a database, you can store them as a successive sequence of events that change the state of your particular business entity. Canonical example is, of course, a bank account. Your bank account is not your, my English sucks today, I forgot the word. It's not the number you see when you look at your ATM and ask how much money do I have left in my bank account. It's not your balance, right? Your bank account is the succession of events, succession of deposits and withdrawals out of your bank account. And putting all of those together gives you the balance. And there are a lot of benefits to storing your data in that way. Observability is built in, as is auditing. Right? If you only save what happened as opposed to the results of that thing happening, then you have observability built into your system. And it lets you scale, read, and write use cases independently, which is the impetus for the CQRS pattern, on which there was a talk yesterday at this very conference. The apparent downside of this is that it precludes full consistency. Right? If you store events, then ostensibly you can't get full consistency out of it. You can only get eventual consistency out of your systems. I submit that that is a good thing, because unlike the narrow field of software engineering, virtually nothing in life is fully consistent. No business that has more than, say, one branch is fully consistent. No bank account, no banking system is fully consistent. They all have to deal with the laws of physics and the reality that in order to provide service, you have to give up consistency in order to get availability. Right? The world we live in is essentially eventually consistent. So giving up on this facade of full consistency that you're used to from your traditional database systems and your traditional architectures only ends up with systems that are actually easier to reason about and work more reliably and faster at that. The last use case for events is modeling workflows. This is what's called the saga pattern and is a very big topic that's totally outside the scope. Suffice to say that for the most part, sagas give you what you need or what you used to want out of database transactions at a fraction of the cost. And they're not super complex to build. Again, large topic, we have no time to go into it, but I would highly recommend digging into the saga pattern. It is a very, very useful tool to have in your toolbox. The bottom line is, for my money, you should sweat the principles, not the implementation details. For the last 10 years, we've been mostly focusing on what it entails to build a microservice-based system. We've been talking about RPC subsystems and monitoring and circuit breakers and all of these things. And all of these things over the last few years have been commoditized. If you're building a microservice framework for your organization, you're probably wasting your time and wasting your company's money. A lot of these tools can now be taken off the shelf and integrated into your microservice substrate, and they will do a much better job than you would have done 5 years ago. So instead of spending the time learning about how to implement circuit breakers and how to do HTTP 2.0 reliably and efficiently, and whether you should serialize stuff as JSON or protobuf or thrift, just pick any one of those tools and spend your time investing in studies. Spend your time learning the laws of physics, namely the CAP theorem and various trade-offs that are involved with it. Spend your time learning how to model your domains, how to do event storming, which is a nice technique for starting to draw those boundaries around your different contexts. Learn about event sourcing and CQRS. Learn about sagas. If you spend your time doing these things, you'll be much better off. You'll end up building systems that are more performant, more reliable. You will enable your organization to grow faster. You will be able to build additional product lines based on your pre-existing products faster and more reliably. You'll be better off all around. I will leave you with these two links. One of them is totally a shameless plug, by the way. But first, there is this talk by the then CTO of Guilt, Michael Bryzek, which is called Design Microservice Architectures the Right Way. He's dishing out a lot of wisdom there. And then if you're interested in event sourcing, there's my own talk called An Abridged Guide to Event Sourcing, which will hopefully be useful to you in getting started. And I can flat out guarantee if any of these things sounds hard or sounds scary to you, they actually are not. As soon as you start looking into how to actually build these systems, you will find that they are a lot simpler. Not only than you think, than that you're used to from traditional architectures. And with that, we are out of time. Thank you very, very much.